Okay, gravitation. So what I have here is something heavy like this backpack, which I call mass 2. And then I have this other very heavy backpack, and I call it mass 1. I'm just assuming that actually the two have the same kind of mass, so I call this mass 1. And now the gravitational law says that if you have mass 1 and mass 2, and you have a certain distance between the two, which you always will have, because since I'm kind of walking in between here, I guess I have to put my distance r. Usually distance r means radius, but it says r over d either way. I have a certain distance between here, so I have mass 1, I have mass 2, I have a distance in between here. I will get the gravitational force. That means these two backpacks will attract each other. If we give them a little time, they would actually move towards each other, except there is static friction here, so they're going to stick on the tables here after all. And besides, they're actually attracted to everything else as well here. So even though they try to move to each other, well, they would be attracted to me or to that wall or to that wall and so on, because gravitational laws just says two masses attract each other. It doesn't say what masses they have to be. I just want to use these two backpacks here as an example. So let's assume that they drift towards each other because between the two they have a gravitational force, which I call F1 over here and F2 on the other side. And if I drew these correctly, and you may come closer with the camera too, if you want to, me too. If I drew these correctly here, these are actually the same size for two reasons. One is the gravitational law says I multiply mass 1 with mass 2, and if I do it this way, or if I multiply it this way, I come up with the same force. So that's one reason why the force between the two is the same. And the other reason is that because of the action-reaction principle, Newton's third law tells us that the force is the same over here as it is over there, just in the opposite direction. And that's what it shows as well. Okay. What happens to them? Well, the two are attracted towards each other because of the gravitational force that they exert on each other. And if I go to Newton's second law, what I do is I divide by the mass of the backpack, and I come up with an acceleration. If I assume that the two backpacks are the same mass, I come up actually with the same acceleration. And now they drift to each other. It will take them a long time because the gravitational constant in the law is so small, in the neighborhood of like a few hours or so. If there wasn't any friction and if there weren't any masses out here, if I just put them into space away from any kind of large attracting mass, yeah, it would take them a few hours to drift that kind of distance here, 5 feet or 1.5 meters. Okay, I'm going to change the thing here. I'm going to take this backpack away, and I'm going to put this little guy here. What is the name of it?
Raphael.
Raphael, and apparently that's a Ninja Turtle, which means that I have to change a few things. This is actually show to a certain extent, which means I definitely have to change the mass. I'm not having a large mass here anymore. I'm having a small mass. So here's a small mass. It's not gonna, no, that's okay. And I have a big mass over here. I have a force between the two. And the force is still the same. I mean, because of the mass here, the overall force is smaller, but it's the same force over here, same force over there, for the same reason I just mentioned. Newton's third law says equal and opposite forces equal opposite forces. And the gravitational law says mass 1 times mass 2, respectively the other way around, but that's the same way. Or that's the same result. What's different is that over here I divide by the small mass and I come up with an acceleration. Over here I divide by a large mass and therefore I come up with a small acceleration. So small acceleration here, large acceleration here. And after a while these two are drifting towards each other. This one here will drift less because it has less acceleration. This one here, oh, no, it's hidden here, will drift more because it has small mass, it has a larger acceleration. The same thing happens for these two, for example. The Earth and the Moon. So I could take my labels out here and gravitational force. Not quite to scale, actually the size is to scale, but I would have to put this approximately oh, how much is it, 20 feet away or so from each other, but then you know the camera isn't wide enough for that. So here I have a mass here, I have equal and opposite forces, but the difference is the moon has much less mass, therefore larger acceleration, and therefore we consider the moon orbiting us. Not the full story. Full story would be that the moon is also moving forward because of its inertia, and the inertia combined with the gravitational attraction actually gives us the orbit. But I would do that at a different time. This is just about acceleration. Gravitational law just says that you have two masses, they attract each other. So I have these two masses attracting each other here, and any one of these masses attracting Raphael, the Ninja Turtle, or the backpack over here, or me, or you and me attracting each other gravitationally. And yeah, that's what it basically says. I've got another Earth globe here, where I put these two little Lego figures here, one in Alaska and one in New Zealand. And yeah, it's not that this here is necessarily down under, or I guess it is, but the gravitational force is between each one of these and the Earth, which is towards the Earth's center. So yeah, this one is stable here, and the other one is stable as well. It just looks fine in the classroom. Any kind of other object, anything that has mass, like Mars, has a mass, and therefore if you bring anything else close, like this Mars rover here, yeah, it will stay, because the two gravitational attract each other. Same thing, Jupiter and this one. Two gravitational attract each other, so the rover could actually drive around on Jupiter, except that it's a huge atmosphere, so it would actually keep falling through the atmosphere of Jupiter. So as long as you have mass, two masses, they will attract each other. And that's basically the gravitational law.
This is about the gravitational law. So we're going to look at the one at the bottom here first. There is a gravitational force acting between these two objects, and I just made them in some kind of arbitrary shape, gave them some arbitrary color. There's a mass 1 here, there's a mass 2 here, they have a certain distance in between, and therefore they will experience a gravitational force. Notice that with m1 times m2, or m2 times m1, the gravitational force is the same, and you see that the arrows are the same, just in opposite direction, which also goes with Newton's third law that says there is an equal and opposite force on each of the objects. I'm going to run this here. As you can see, the closer they get, the higher the larger the force is. The acceleration here depends on that force, which is the same for both, divided by the mass of each object. These two masses here are virtually, the two objects have virtually the same mass, so therefore the acceleration is virtually the same, and you probably don't see a difference. And at some point, the acceleration and the force becomes so large that it gets out of the picture. So here we have a small object. Here we have a large object, meaning a large mass, and a small mass. Notice that the forces on either one of them are the same, because that's what Newton's gravitational law says, and it's also what Newton's third law says, that there are equal and opposite forces. I'm going to let this run, and as we can see, the smaller mass has a larger acceleration. Still has the same force, as you notice, but it has a larger acceleration because of Newton's second law, which says we divide by a small mass, so we get a large acceleration. We divide by a large mass, we get a small acceleration on the larger object, and that, of course, is what we saw. And then they're just going to overlap, bounce off each other. So there is again. So here we have now 3 objects together, and when I let this run, notice that the force, the gravitational force between each of these 2 objects is the same. So this gravitational force is the same as this one, this gravitational force is the same as this one, and this little gravitational force is the same as this one. Depending on the masses of the 2 objects, that's why we have the smallest force between these 2, because these are smaller masses, and the largest gravitational force between these 2 objects because they have the largest masses in this trio. Furthermore, the gravitational force, of course, depends on distance. So the closer they get, the longer these arrows get. Because now these 2 objects, for example, are closer, so their gravitational force is larger. Notice that the direction also changed because this one here is at a different angle now from this one. Also notice that with 3 objects, 3 mass, I'm going to reset this here, that with 3 objects, it becomes actually relatively complicated, which is why in astronomy we're giving an introduction of what's going on. We like to focus at only 2 objects because it makes it easier. So here we're looking at the planets in the inner solar system, and of course they orbit the Sun. Respectively, they are attracted towards the Sun, and the Sun is attracted to them, and they all attract each other. But as I had mentioned, we like to focus at 2 objects at a time because it makes it easier. And fortunately, the Sun is such a massive object that we can just focus on the Sun and any one of the planets, just one of them at a time, and we come up with a nice orbit for Mercury, or a nice orbit for Earth, or a nice orbit for Mars or Jupiter, and so on, because the gravitational force between any 2 of the planets, for example Mercury and Venus, is so small compared to the gravitational between the Sun and Venus, respectively the Sun and Mercury, that it can be neglected, and we just look at 2 objects at a time, mainly the Sun and a planet. Or if we have moons going, where we look at moons orbiting around planets, we just look at 1 moon around its planet at a time. It just makes it easier. There will be one exception later on when we look at the moons of Janus and Epimetheus as they orbit Saturn, but that'll be in a later chapter. So what we have seen so far is that 2 masses attract each other. What's interesting for astronomy is that not only do they attract each other like this here, and then they bump into each other, as it's suggested here, but of course objects are orbiting. In order to avoid that they bump into each other, what we would have to have is that one or both objects have some kind of initial velocity. I'm just going to try this here and see what happens. So this object here likes to fly off, but of course it's being pulled towards the left, and that will change its velocity slightly to the left, and then it wants to go up. But then it's being pulled towards the larger object, and so it's going to go to the upper left, and so on, and we're going to get relatively quickly, we're going to get an orbit out of this. There it is. I'll discuss this in a little bit more detail once we get into orbits. We also see nicely here Kepler's second law at work. Notice that the force between the 2 is the same. We consider that the small mass is orbiting the large mass because it has such a large acceleration, that green arrow that we can see, while the acceleration on the large mass is so small that we can virtually neglect that it's doing something. And by the way, I don't know why it vanished here. The software that I'm using isn't absolutely perfect, and all of a sudden the other object was gone. Anyway, we see what's going on here. This recording shows you how to work with this gravitation applet. First, go there from within the lab sheet, so I'm going to hit Control, click on there, and I'm going to get it. There, that's what it opens. Now you click on Run Now, and there's the applet. Okay, let's see what it says we're supposed to do. As I said, I'm going to do just a couple of 3 examples. I don't think I'll be able to fit everything in here. There we go. Okay, I'll actually leave this off the screen here so I can read it myself. Alright, it says select the preset Sun and Planet, so I'm going to do that. Now it says change the y velocity of body 2 from 120 to 140. So here's body 2 and I'm going to change it to 140. What is the shape of the planet's orbit? Of course, at this point I'm going to start it. And there we go. There's one full orbit. Okay, and now it asks, what is the shape of this planet's orbit? Well, this is an ellipse. Which law says it would be of such a shape? Kepler's first law. Why does the Sun describe an orbit as well? Well, because the two attract each other gravitationally. And so it's not just that one is going to orbit around the other, but the second one is also going to orbit around the first one. So both describe an orbit because of the gravitational attraction between the two. Why is the Sun's orbit smaller? Well, because the Sun has a much higher mass than that of the pink Earth in this case. And you can see that the mass is here 200 versus 10. And because of the smaller mass and Newton's second law, the acceleration is much less on the Sun than it is on the pink planet, and so the resulting orbit is much smaller. Okay, let's do the second one here. Sun, planet, and moon. It says let it run the way it is. What kind of shape does the moon's orbit around the Sun seem to have? Well, it could be kind of described as a flower-shaped orbit. Which of the other two bodies exerts a gravitational force on the moon? Well, since we know the gravitational law, both of them, both the Earth as well as the Sun, exert a gravitational force on the moon, and in turn the moon, of course, exerts a gravitational force on both the Sun and the Earth. That's Newton's third law as well as the gravitational law. Now turn off the show traces. So I'm going to do that. What kind of shape does the moon's orbit around Earth have? Well, looks like either a circle or an ellipse. Okay, I'm going to do one more example, which is the last one, the one with the ellipses. Second to the last one. It says check the show traces, show grid, and tape measure. Show traces, show grid, tape measure. Let it run the way it is. You now see 3 important astronomical laws at work. Name them and write them down in short form. Well, we see Kepler's first law, which is planets orbit on an ellipse, or any kind of body orbits on an ellipse. We see Kepler's second law. For example, look at the green one. The furthest it's away, the slowest it is, and the closer it gets, the faster it gets. And we see Kepler's third law, which says that the distance and the period of a planet are kind of proportional. The larger the orbit of a planet is, the longer it will take it to orbit. Respectively, you have the p squared over a cubed or a cubed over p squared relationship. Okay, now it says reset and change the slide bar's accuracy to 1 unit. So put this at 1 unit here. Stop every time a body completes the one orbit, and I'm only going to do it for the pink one here. So I'm going to start it and then stop it when it's done, right there. Okay, I cannot do it any more accurate. I'm measuring time of 2.3. It says measure the horizontal width of each orbit and divide by 2. That yields the semi-major axis of each orbit, which is the average distance from the Sun to each body. So I'm going to measure it here, right there to there. Okay, that reads 141, and I'm supposed to divide by 2, so I'm going to come up with 70.5. And then the period comes out to 2.3, because it's only two significant figures anyway. I could just say that my distance is 71. So my average distance is 71. My period is 2.3. By the way, if I go just a little bit further, right there, see, I cannot even click that accurately, and 2.3 is just short of one orbit. 2.4 is actually quite a bit further, so 2.3 is a good number for the period. So that's what I'm going to plug in here, 2.3. These are kind of arbitrary chosen units by the applet itself, so they don't have any seconds or something attached to it. And I said this one here is 70. And now on the calculator on the side, I'm going to do 71 cubed divide by 2.3 squared. So it's 71 cubed divide by 2.3 squared. Enter. That's around at 68,000. By the way, had I used the 70.5 earlier, I guess it's going to be a little bit different. 2.3 squared. And that would be around at 66,000. You would have to keep in mind that you only have two significant figures here. So 68,000, 66,000, there's already a little bit of an error in there. I'm going to plug that in here, so 68,000. And what would you have to expect for the blue and the green one? Well, basically the same, because that's what Kepler's third law says. And with that, I conclude this introduction to how to work with the applet on gravitation. This is about orbits, and while I explain orbits, I will also talk about the law of gravitation and apply Newton's laws as well. So here we have the Sun and the Earth. The Earth has a certain velocity, in fact 20 miles per second or 70,000 miles per hour. It has also an acceleration towards the Sun. That acceleration is relatively small, actually, 0.006 meters per second squared, if you want to compare that to the 9.8 meters per second squared of gravity here on Earth. But it is caused by the gravitational attraction by the Sun on the Earth. In turn, the Earth also attracts the Sun, and I show this in just a moment. First, this is how we get an orbit due to the attraction of the Sun on the Earth, and for simplicity I will keep the Sun fixed here, but just to show that the Earth in turn attracts the Sun, here we have, as you can see, the Sun is also kind of a little bit orbiting, being attracted by the Earth. So that's Newton's third law as well. respectively, the law of gravitation is also what it says, that the two attract each other. But as I said, for simplicity, we just keep the sun fixed, so that we just have the Earth going around it. The Earth would just move on with at 20 miles per second because of its inertia. What happens if the Earth wouldn't have any velocity? Well, in that case, all it would notice is a gravitational attraction by the Sun, and it would fall towards the Sun. Here again, and I also can turn on or take the anchor away from the Sun, and the two attract each other. And I guess you don't see the Sun actually moving at all because it has such a large mass. Here comes into play, I'm going to pause this here for a moment. Here comes into play that the Earth recognizes the same gravitational attraction towards the Sun as the Sun is attracted towards the Earth. That's the law of gravitation as well as Newton's third law. As far as the acceleration is concerned, here Newton's second law comes into place. With the Earth's much smaller mass, it has a much larger acceleration. With the Sun's much more mass, it has a much less acceleration. And therefore, in this animation, we don't see it moving at all. Back towards keeping the Sun fixed here, and the Earth moving because of its inertia. It has this velocity, and it's being attracted to the Sun, so the Earth wants to move up, but it's attracted towards the Sun, so it moves a little bit left, but then it moves to the upper left, and it's being attracted to the Sun, and then moves to the upper left, and it's being attracted to the Sun. So we basically are going to get the following. Moving up, but it's accelerated to the left, upper left, 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 and down, and this is a little bit too fast for me here, so I'm going to stop this here. So here it moves up, but it's attracted towards the left. Now it moves to the upper left, but attracted towards the lower left, always towards the Sun. Now it's moving to the left, but it's attracted down. Now it's moving to the lower left, and it's attracted down to the it's moving down, but it's attracted to the lower right, and so on. So those two things combined, the planet's inertia and the attraction towards the Sun, that make the orbit. Wanting to move in a straight line, inertia, being attracted towards the Sun, the gravitation, that those two combined make the orbit. We can also see that because of that, the Earth is moving in a almost circular orbit actually here, maybe slightly ellipse. Notice that the Sun is not at exactly the center, obviously, but if you look casually at this here, you probably cannot distinguish this orbit, this kind of elliptical orbit, from a circle actually. We just see that the Sun is sitting in one of the two foci, not the center of it. Lastly, I changed our system here a little bit. I made the orbiting object here much slower. And so, for example, we have a moon around a planet like Nereid around Neptune. And because it's slower when it orbits, it actually is a quite elliptical orbit. As we saw earlier, the Earth's orbit is so ever slightly elliptical that we cannot distinguish it from a circle. But for this one here, so same things apply. Because of its inertia, it wants to go forward, and because of gravitation, it's pulled into this orbit. We can also see easily Kepler's first law, it's an ellipse. We can see Kepler's second law, that it orbits really fast when it's close and slow when it's farther away, respectively. Starting over again, when we put the acceleration in here, we can see that when it's really close, the acceleration is huge, because the gravitational law says that because of the distance we get a larger force, and then Newton's second law, we calculate the acceleration and we get a huge acceleration. That's why you see these overproportional acceleration vectors. This is about orbits, and while I explain orbits, I will also talk about the law of gravitation and apply Newton's laws as well. So here we have the Sun and the Earth. The Earth has a certain velocity, in fact 20 miles per second or 70,000 miles per hour. It has also an acceleration towards the Sun. That acceleration is relatively small, actually, 0.006 meters per second squared, if you want to compare that to the 9.8 meters per second squared of gravity here on Earth. But it is caused by the gravitational attraction by the Sun on the Earth. In turn, the Earth also attracts the Sun, and I show this in just a moment. First, this is how we get an orbit, due to the attraction of the Sun on the Earth. And for simplicity, I will keep the Sun fixed here, but just to show that the Earth in turn attracts the Sun, here we have, as you can see, the Sun is also kind of a little bit orbiting, being attracted by the Earth. So that's Newton's third law as well. Respectively, the law of gravitation is also what it says, that the two attract each other. But as I said, for simplicity, we just keep the Sun fixed, so that we just have the Earth going around it. The Earth would just move on with at 20 miles per second because of its inertia. What happens if the Earth wouldn't have any velocity? Well, in that case, all it would notice is a gravitational attraction by the Sun, and it would fall towards the Sun. Here again, and I also can turn on or take the anchor away from the Sun, and the two attract each other. And I guess you don't see the Sun actually moving at all, because it has such a large mass. Here comes into play, I'm going to pause this here for a moment. Here comes into play that the Earth recognizes the same gravitational attraction towards the Sun as the Sun is attracted towards the Earth. That's the law of gravitation as well as Newton's third law. As far as the acceleration is concerned, here Newton's second law comes into place. With the Earth's much smaller mass, it has a much larger acceleration. With the Sun's much more mass, it has a much less acceleration. And therefore, in this animation, we don't see it moving at all. back towards keeping the Sun fixed here, and the Earth moving because of its inertia. It has this velocity, and it's being attracted to the Sun, so the Earth wants to move up, but it's attracted towards the Sun, so it moves a little bit left, but then it moves to the upper left, and it's being attracted to the Sun, and then moves to the upper left, and it's being attracted to the Sun. So we basically are going to get the following. Moving up, but it's accelerated to the left, upper left, 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 and down, and this is a little bit too fast for me here, so I'm going to stop this here. So here it moves up, but it's attracted towards the left. Now it moves to the upper left, but attracted towards the lower left, always towards the Sun. Now it's moving to the left, but it's attracted down. Now it's moving to the lower left, and it's attracted down to the. It's moving down, but it's attracted to the lower right, and so on. So those two things combined, the planet's inertia and the attraction towards the Sun, that make the orbit. Wanting to move in a straight line, inertia, being attracted towards the Sun, the gravitation, that those two combined make the orbit. We can also see that because of that, the Earth is moving in a almost circular orbit actually here, maybe slightly ellipse. Notice that the Sun is not at exactly the center, obviously, but if you look casually at this here, you probably cannot distinguish this orbit, this kind of elliptical orbit, from a circle actually. We just see that the Sun is sitting in one of the two foci, not the center of it. Lastly, I changed our system here a little bit. I made the orbiting object here much slower. And so, for example, we have a moon around a planet like Nereid around Neptune. And because it's slower when it orbits, it actually is a quite elliptical orbit. As we saw earlier, the Earth's orbit is so ever slightly elliptical that we cannot distinguish it from a circle. But for this one here, so same things apply. Because of its inertia, it wants to go forward, and because of gravitation, it's pulled into this orbit. We can also see easily Kepler's first law. It's an ellipse. We can see Kepler's second law, that it orbits really fast when it's close and slow when it's farther away, respectively. Starting over again, when we put the acceleration in here, we can see that when it's really close, the acceleration is huge, because its gravitational law says that because of the distance we get a larger force, and then Newton's second law, we calculate the acceleration and we get a huge acceleration. That's why you see these overproportional acceleration vectors. Here we have a system of two masses in orbit that are closer in mass. For example, Pluto and its moon Charon. And as we can see, now this time I didn't fix the central object because the masses are closer, so their accelerations are closer as well, and the central object actually does move. So you can easily see Newton's third law at work, the two orbiting each other. This view includes the common center of mass. Notice that it stays the same as the two orbit each other. The same would apply to, for example, the Earth and Moon system, but the center of mass would be much closer to the Earth because the Earth has a much smaller acceleration due to its much larger mass than that one of the Moon. Again, this all ties in with Newton's third law, Newton's second law. So here we have Earth and Mars orbiting the Sun, and because the Earth is closer to the Sun, it has a larger gravitational force, larger acceleration, and so that overall, and because of its larger speed as well, produces a faster orbit than Mars orbit does. We can also again see that both of these are ellipses, and if I start over again, then we can nicely see that, of course, the Earth is moving much faster around the Sun due to Kepler's, or which illustrates Kepler's third law. This recording is about gravitation and planetary motion. The way this particular software works here is physics simulation software is that by default it's that there's gravity pointing down, and that's what it says here, vertical. So if I just hit the run button, that's out of the picture here, then everything is just going to fall down. So I have to change the way gravity works in the software. So I changed it to planetary, and this is not the typical gravitational constant, which is really small, 10 to the negative 11, but I changed it to a value of apparently 40 because that works really well in the software with the time given in the software, because otherwise it would take years in order for just one orbit here. Okay, anyway, so that's the way it looks like. And so I hit OK on this one, and then I hit the run button, and if we just leave these two here, then they will attract each other gravitationally and slam into each other. Notice that I made these blue here as if it was the Earth, and gray as if it was the Moon. You notice that the Moon apparently accelerates faster towards Earth. The force on the two is actually the same, but the acceleration on the Moon is much larger, and that is because the mass of the Moon is much smaller. I gave it here 0.003 kilograms. Again, I made these. I just made up these masses, these numbers here, so that it works pretty well in the simulation here and doesn't take too long. I don't have to fiddle around it too much. Apparently, the mass of the Earth is 0.3 kilograms, so 100 times as much, and that's what you saw is happening. That the Moon, because of its smaller mass, is accelerated easily towards Earth, while the Earth moved just a little bit. Okay, let's go back to the Moon and actually do give it some speed, some velocity to the left here, because without it they will just slam into each other. And now that combined with the gravitation, I hit the run button, produces the orbit, because what's happening here is that the Moon starts moving this way, but then it's gravitationally attracted to the Earth, moves this way, gravitationally attracted, and that changes the direction, and it also changes the velocity vector, just as you go into a curve, and the friction between the tires and the road changes your direction and giving you a centripetal force. In this case, that would be the Moon orbiting the Earth. Okay, I'm going to hit the reset button, and let's just change a few things. For example, I'm going to put more mass on the Earth. So instead of 0.3, I may have 0.6 kilograms. And the Moon is still orbiting, but in a tighter orbit, because now the gravitational force is larger. So I may increase the Earth's mass even more. There we go, and an even tighter orbit, but it's still orbiting. By the way, I kind of forgot here a moment ago. Let me go back to 0.3. You saw it, but I forgot to point it out, that it's not only the Moon orbiting the Earth, but it's the Earth also orbiting, kind of making this wobble here, because it's attracted with the same force towards the Moon. It's just that its little wobble or orbit is not as much as the Moon's is, because it has quite a bit more mass, 100 times in this case, the way I set the numbers. Okay, so more mass produces that. What about less mass? Okay, what about if we decrease the mass? So I'm going to use 0.2, for example. Let's see what happens to the Moon. And sure enough, it makes a bigger orbit. In this case, actually, I believe the moon, as it went out of the picture, could possibly be lost. I didn't check that out before. I'll see in just a moment if it does come back. Because in this case, maybe the tangential velocity was too large that the gravitation of the Earth wasn't able to hold it back. So I think that's what happens, because I don't see it coming back. So apparently in this case, let's not make this too small. There we go. And there, sure enough, the orbit is larger because there is less gravitational force between the two, but it's still in orbit. So the scenario I showed a moment ago actually described escape velocity. Now, the moon is not going to do that, but in order to get, so to say, away from Earth, not from its gravity, but to keep on going in space, Earth's gravity is still slowing it down, but not sufficiently. There is such a thing as escape velocity, that if it's large enough, you're not going to orbit the Earth anymore, but you're going further out. You're still being slowed down by it, but you can keep going out. Okay, let's see, one more thing, and that is, I'm going to put this back to point 3, and we're back to our typical orbit, and alright, hit the reset button. Okay, now what happens if I introduce perhaps something like a black hole? I'll make it black. There we go, and I take this one out. And I put this one here. There's my black hole of the same mass. So 0.3 kilograms. Hypothetical question, what if the Earth turned into a black hole? Well, of the same mass, that is. Well, apparently it's the same mass, so the gravitational force is the same, so the acceleration on the moon is the same, so therefore nothing on its orbit would have changed. And indeed that is the case. Oh, whoops. Okay, what did I do wrong? Oh, I know what I did wrong. I put that Earth out of the picture, and that actually attracted both of them, so I have to delete that actually. Alright, here we go. Here we go. So, because of the black hole sitting there, orbiting the moon actually a little bit as well, nothing of the orbit has changed, because the mass is the same, force is the same, and therefore acceleration is the same and orbit is the same. This is about tides. Here we have the Earth, and over here is the moon. The relative sizes are actually to scale between the two. The Earth with a diameter of 8,000 miles, the moon with a diameter a little bit more than 2,000 miles. The actual distance between the two is not, as it says here, the actual distance between Earth and moon should be 10 times as much. So the moon would be actually out of the picture here. But of course we would like to have it in here, so we're faking that somewhat. But I can move this blurb here out of the way, out of the picture, because we just looked at it and it would be just in the way now as we look at tides. Okay, the moon is exerting gravitational force on every point on the Earth, and in turn the Earth is moving, exerting a gravitational force on the moon on every point. But we're interested in what happens to the water bodies on Earth, so we're just going to look at the gravitational forces that the moon exerts on the Earth, and not vice versa, as I said, because we're interested in what happens to the water bodies on Earth. Okay, so here's the gravitational force of the part of the Earth that is closest to the moon. Here's the gravitational force of the moon exerted on the Earth itself, and notice that this one is shorter, which makes sense because it's further away, and that's what the gravitational law says. It depends on the distance. Here is the gravitational force that is exerted on the other side of the Earth, again because it's further away. Of course these arrows are exaggerated so that we can actually picture them here. Here is the gravitational force exerted towards the bottom. Notice it's about the same length here because it would be the same distance, but it's at an angle because it's pointed towards the moon. Here is the gravitational force exerted on the top of the Earth, or in this part here in this picture, the top, again at an angle. So these are the forces that are exerted on each part of the Earth. So what the moon is doing is it's pulling this part here the most towards it because it's closest. This part here is pulled less towards the moon because it's further away. And this part over here is pulled yet less towards the moon. And we can already see that now we have tidal bulges on the side closest to the moon and furthest from the moon, because we have less force here than we have in the middle of the Earth, and more force here than we have in the middle of the Earth. So that's basically the explanation for tides. If we take this a little further, we can do the following. We can take this force here that is exerted on the Earth and subtract it from each of the other arrows. So I'm going to do that. Subtracting means I turn the arrow around. So as I subtract here, I get this net, and now I can move this one out of the picture. When I subtract this one here, I get this net. Again, I can move this out of the picture. When I subtract this one over here, I'm going to get this net. And again, I can move this out of the picture. When I subtract this here, I get this net force. And again, I can move this out of the picture, and now I can move this one out of the picture as well. So if I take it a step further, then these are the forces that we would have on each part, on each of these water bodies. And then we can see that, well, here we have the water, so to say, being pulled away from the Earth over here as well. Remember the earlier picture we had? The reason is the difference in the gravitational force depending on the distance to the moon. Here we have components that pull the water towards the Earth, and then what the water likes to do is it actually likes to flow over here. So we can take these slabs of water and just turn them. And same thing over here. There we go. I know this looks a little bit funky actually, more so than what I intended. Respectively, actually, these arrows I could leave there, I guess. And then the Earth rotates underneath these tidal bulges. So different parts of the Earth get a tide, get a high tide, and then different parts get a low tide. So if I start this over again, then we would have here a high tide. 6 hours later, we have there a low tide. Another 6 hours later, we have another high tide, so that's a total of 12 hours. Another 6 hours later, we have another low tide. Another 6 hours later, So 24 hours total. We have a high tide respectively. In the meantime, in those 24 hours, the moon would have orbited some. So actually, the slabs of water are not directly pointing, are not exactly here anymore, but they would be kind of here, and these would be kind of here. And of course, this one here would have to be a little bit moved around. There we go. There we go. And that's why we don't have tides exactly every 24 hours, or exactly every 12 hours, but every 12 hours and 25 minutes respectively when we go from one high tide to the over next high tide. We would have them every 24 hours and 50 minutes because the moon has orbited a little bit in the meantime. As an example, I'll calculate here the location of L2 for the moon going around Earth, and L2 would be lying on the far side, and perhaps the interest to put a satellite there would be one that monitors the far side of the moon. The equation looks virtually the same with the exception of this plus right here. There is a minus in the equation that you use, and it comes from that for your equation that you use with L1 lying in between Sun and Earth, the two gravitational forces are subtracted. And here, because Moon and Earth are lying on the same side of L2, the two gravitational forces are added, and really the only thing that changes for the whole equation is that there used to be a minus, and now in my example there is a plus. Okay, so here's the equation. Let's first calculate this one here, 1 plus the mass of the moon divided by the mass of Earth. So for that I looked up the mass of the moon and the mass of the Earth. I divide the two and I add that to 1, and I come up with 1.012316, I guess, rounded, for that coefficient in the middle of the equation. By the way, for the one that you're going to calculate, I divided the mass of the Earth by the mass of the Sun, and I come up with 0.999997, and that's written on the lab sheet, so you don't have to do that calculation. It's already a 0.9997 with that minus in front of the coefficient. Look at the equation. The same as with my factor, the 1.012316, that also has a minus in front of it. So now I'm going to this online calculator for quantic equations, and I'm going to put the coefficients in, and the one for r to the 5th power is 1, and that's what I said in the text. You know, you kind of have a 1 in front of it. Don't put a 0 there because it's not. It's a 1. And then the one in front of the r to the 4 is a -2. The one in front of the r to the 3rd is 1. The one in the front of the r squared, that's a complicated one. It starts out with a minus in front of the parentheses, and then 1.012316. So I finally rounded it. The one in front of the r is a 2, and then the last one is just a -1, and then I have it calculate just to 6 decimal places, and I come up with 1.168168186. But I basically just going to look at the first couple of digits here, the 16, or rounded 17, and that means that L2 is lying 17% further out than what the moon's orbit's radius is. So take the moon's orbit's radius and multiply it by 17%, and that's where L2 is going to be. I'm going to do that here. So the moon's orbit's radius is or semi-major axis actually, is 384,400 kilometers. I multiply that by the 17%, so pi 0.17, I come up with 65,000 kilometers. I found a reference on the internet that looks as follows. So here at this question and answer website, curious.astro.cornell and so on, you can see that they posted 60,000 kilometers, and they call it the Hill sphere, and they explain the Hill sphere being under the influence of one body rather than the other. So that coincides with the number that I came up with. So you have to do the same thing for the L1 point that lies between Earth and the Sun. Notice that I came up with 1.17, and then I used the 0.17 as a percentage. You're going to come up with a number slightly smaller than 1. So for example, if you came up with 0.92, then you would use the difference of 0.08, 8%, as the distance that L1 would be from the Earth. So 8% in that case, if that's the correct answer. By the way, it's not. So 8% of one astronomical unit.